Hello friends, this video is about the experience sharing, and actually I cover some common questions and their solutions. So let's get started to LeetCode. Why do we do LeetCode? Because we need to practice the problem solving abilities. So first thing first, how can we get started to LeetCode? We first need to have the basic knowledge, because if we do not have the essential knowledge, we can never solve the questions. Then we should practice more to see many problems patterns. So next time when we see a new problem, actually we can use our previous knowledge to solve it. The whole idea of practicing LeetCoding is not to memorize the problems and the solution. What we need to learn is about the problem-solving skills, how to analyze a problem, and how to approach that. So first, I will introduce some basic knowledge I think that is essential. First part is the data structures. Of course, you need to be familiar with all the data structures and their implementations in your main programming language. Let's see, first is arrays, also the string, because we can treat the string as the char arrays. The next is the list. List is a container that have the order by their adding order, and they may have the duplicates. That's the difference between the list and the set. Set is unordered, but you can have some order sets like the tree sets or linked set, or maybe this name in Java, and they cannot have the duplicates in the set. Then the stack and the queue. Stack is last in, first out. Queue is first in, first out. At the deck, we can do the offer and pull in two ends. This is just a variation of this queue. And the most frequently used is the map. And basic map is just to map a key to its value, and the the time complexity in the base case is big O1. But if we do not have a good hash function and the values distribution is not good, we may have the lookup time complexity of the big O(n). But usually we can see the lookup time complexity and big one, which is a constant. And also the heap is very commonly used. It have the max heap and minimum heap. For the max heap, for example, the top of the heap is the maximum number in the whole heap, so it's greater than its children. For this data structure, we need to familiar about the time complexity of some very common operations, like the add, remove, contains. What's the time complexity for each data structure in your used language? And we also need to know the underlying implementation. Like the list interface in Java, we have two implementations. One is the array list, the other is the linked list. We use array to implement the array list, and also use the linked list to linked list to implement the linked list node actually. You should consider about their suitable scenarios to use these data structures and their characteristics. So now let's see some very common questions and the very common use algorithms. Actually, the algorithms are associated with the data structures. Let's see in problems about the arrays. I think the most common use algorithm is the 2 pointers. We maintain 2 pointers, which is the low and the high. We may start from both sides or we start from 0. And also we have a sliding window algorithm. This is very common, and we have many questions related to sliding window, like the longest non-repeating characters. Actually, I may explain this problem before. We just maintain a window, use the low pointer and the high pointer, and to add some constraints to maintain that window. The second algorithm is binary search. Actually, I think they have many variations of the binary search, and there are many scenarios we can use binary search, not necessarily the original sorted array. If you remember, we have seen a problem related to the rotated sorted array that we also use binary search. So maybe sometimes they have other characteristics you may to figure out that we can use a binary search. And I think there are basically two kinds of binary search. One is we know there is an answer, like find the first bad version. If we are given a version list and after a specific version, the following versions are bad, we need to find the first bad version. We use while low less than high, and in the end we return low. In this case, we know we must have an answer. So finally, actually the no equal to the high. The second case is that we do not know whether we have this value, so we need to search the whole space. You should notice that this is no low less or equal than high, and finally return false. The whole idea of the binary search is that every time we just shrink the search space to half of the previous search space, so time complexity is log n. Also, the arrays problem usually combine with map because the lookup time complexity of map is big O1. There is another big part of the subarray problem. You should consider to use the prefix sum. Because we knew a DP array, and DPI means the sum of the array from index 0 to the index I, and the DPJ means the sum of the array start from index 0 to index j. So how do we get the sum between the I to j? We just use DPJ minus DPI, but you should consider about the size of the DP array. Usually we use the n plus 1 because to handle the empty array. So dp0 just equal to 0, which means we do not include any elements in the previous array. So when you see subarray, you should think about the prefix sum. Another part is the quick select. There is many problems in LeetCode is related to the k length. We need to get a k length like the smallest element in an array, unsorted array. Actually, they use the idea of the quick sort. So if in the partition function, we get the pivot grade, the time complexity should just be a big O n, which is linear. but actually this is an ideal case. This is the array part. And this is stacks. To be honest, I think a stack is very hard to think of. If you have never seen this problem before, stack may be very hard for you to think out. So you need to be familiar with some very classic monotonic stack problems, like the maximum rectangle and the next greater elements. This is much easier. We need to find the next greater elements in an array, and we maintain a monotonically increasing stack. We start from right to left. I have explained this problem before. You can search in my channel. Also, the very classic trapping rainwater problem. But actually, the optimal solution is you use 2 pointers, not use the stacks. But you should know that sometimes stack is associated with the depth first search, because sometimes we need to explicitly use the stack. Because when we use a depth first search, we implicitly use a stack, which is called stack. Queues is frequently used in the breadth first search. For the graphs problem, I think you should. I think the hard part is that you need to figure out this is a graph-related problem. Sometimes it's very hard to figure that. Like you give 2 sentences, you need to find their similarities. You should do some abstraction to treat that problem as a graph problem. But once you figure out it's just a depth first search or breadth first search, you may mention the unified, but actually unified, all the problems can be solved by unified, can also be solved by depth first search or breadth first search. Sometimes you may use the Dijkstra's algorithm, but it just have some difference between the breadth first search. We use a priority queue. We also use a distance array, and every time we pull something from the heap, we update the distance array. Another important part is the backtracking problem. The core idea of the backtracking is that you try every possibilities and try to get one correct answer, or you need to demonstrate all the correct answer. So you need to print all the parts. Some very basic backtracking problems is the permutation and the subsets and the combination sum. And the partition equal subset sum is like the combination sum. You need to figure out the given array whether we can partition that to 2 subsets and they have the same sum. Combination sum is given array, you are given a target. You will try to find how many combinations can you get their sum equal to the target. There is some difference between the permutation and the subsets you need to figure out. Also, they may have the duplicates. When they have duplicates, you do not wish to get the duplicate result in your permutations or subsets, so you need to skip the duplicates. Actually, there are 2 problems that are fairly hard, which is the n queens and the Sudoku. You can try them in LeetCode. Once you have handled the idea of the backtracking, you can solve these 2 problems. The last part is the dynamic programming. Actually, it is a very high-level problem. Sometimes it may be hard to think of it. One is the knapsack problem. Like the perfect squares, you want to get the minimum squares to that sum up to a given number. So we will try to minus that square from the number. Actually, the code changes are very, I think it's a very typical pattern. One is you need to calculate the total ways to make up the sum. And also you want to find the minimum coins you will use to make up that sum. This is also two dynamic programming problems. Another kind is climbing stairs. You can once get up one step, or you can get up 2 steps. You want to find out if you want to get the step 10, how many ways can you get there? Actually, they are the same. This is the similar problem. So decode ways. Given you a string, we are asked how many ways can we decode the string like this. This is another big part is the string related problem. Actually, I think it all starts from the distance and the longest increasing subsequence, longest common subsequence. We use a 2D array and try to, for the edict distance, with 2D array and try to fill that table. This problem I have explained yesterday is also like the edit distance. We use a 2D array and we iterate these 2 strings and iterate one by one, and we base the current answer on the previous saved answer. This is the big characteristic of this DP problem. The following results are based on the previous results. Another part is the 2D matrix. Like we want to find the maximum square in a 2D matrix. We just need to get the length of the square. We want to cache the intermediate answer and the range query sum. We also need to actually, I think it's erased from the prefix sum problem. This is the 2D problem. So we need to cache the accumulated sum in the row and the column. We also solved this bomb enemy before. We cache the result from left to right. And the unique parts, we need to find the total weight. The total weight start from left bottom to the right top, and we need to calculate the top weights. This problem, or either we need to cache the intermediate results, or we accumulate some sum. So when you find you need to repeatedly calculate some problems, you should think about the dynamic program. Maybe you should cache some results. Also, this idea usually used in depth first search when you need to cache some intermediate results, other than every time calculate again. And this is, I think, is the 3 hints that you may think about DP. One is you just need to calculate the total weights, other than print all the parts. Backtracking, just like you need to print all the parts. Dynamic programming just need to print the total weights, or you just get the answer true or false, like whether these 2 strings are matched. And get the maximum or minimum steps, like the minimum coins needed to make up that target sum. And the rest part is the greedy algorithm. Actually, it do not have very specific hints, but maybe you will think about sort. We just pick the maximum or the minimum equally, which is a greedy algorithm. In this case, we may always use the heap or just a sort. like the top K problem, we can use the quick select, and we can also use the heap problem, heap data structures. Like the problem I explained before, which is the campus box, we pour all the combinations into the heap and or offer all the combinations into the heap and then pour them. And this is a classic heap problem, merge k-sorted list. We offer all the k-sorted lists into the heap and pull one by one. And we pull that, see whether it has the next list. If it has, we offer it into the heap again. Basically, this is the classic problem I can think out, and the techniques you may use to solve a problem. Maybe in the future I may think about more problems and the solutions. I will add them. So this is like the first part. Thank you for watching. See you next time.